differences and some similarities about, we talked specifically about solids in 3.2, and we did talk a little bit about vapor pressure and some liquids parts. But today we're going to compare better, a little bit more, the differences between solids, liquids, and gases to just define things a little bit in more detail. So we can categorize solids into two different classifications, crystalline and amorphous. Crystalline structures have a highly regular arrangement, and amorphous solids are considerably disordered. So has anybody ever seen, for an amorphous example, has anybody ever like opened up a candy bar or like saw chocolate and it had like the discoloring, or it might be like little like ashy or kind of whitish? That when you're making chocolate stuff with pure chocolate, they do a method that's called tempering, which it cools down the chocolate slowly, and what happens is the solids in the chocolate, if you do it slowly, it will get ordered and become crystalline. But if it goes too fast, then that would be considered amorphous. And so that's why it looks all distorted and not colored right and all that kind of stuff. So amorphous would be disordered like that kind of chocolate, okay? Crystalline structures could be all kinds of things. It's anything with a crystal-like structure. So water has a crystal-like structure, like diamond has a crystal-like structure. It's very ordered. Sodium chloride is a crystal. Sugar is a crystal. They're very ordered points. The position of the components in a crystalline solid are represented by a lattice, which we talked about this briefly before, which is a 3D system of points that designates the positions that make up the substance. And the smallest repeating cell or unit of the lattice is called the unit cell. This is, remember we'd have that homework problem that you guys were like, Michelle, how do we do this? And I had to do it on the board with you. It looks like these things right here. Yeah, sound familiar? Yeah. No, we're just talking about it. Okay, so remember, these are the space filling options that show you how much of each portion of each atom are involved. But the lattice part shows like the whole thing. So I've got some models that were made in previous years. So this is a poorly made lattice, like the simple cubic is. I did not make this, a student made it.
But do we need to make them?
No, because I already have enough poorly made ones, so I don't need more. The structure of crystalline solids are most commonly determined by X-ray diffraction.
Wait, is this still recording?
Yeah.
Oh. You're just going to roast us live?
It's who I am. It's who I am. Okay.
I can't wait to watch this. What are you going to watch it, Jake? So I can...
Okay, anyway, so the way that we tell how a solid is formed is by using X-ray diffraction. So what they do in diffraction is they have beams of light that hit the crystal, and then they see how does it come out of the, like how does it bounce off, okay, the diffraction of it. So this picture is in your textbook on page 462. A picture, do you see how it says it's in phase, which I know it's really hard to see because for some reason I didn't include it in your thing. When they're in phase, that means they do the same thing, right? So they're just, the dips, the troughs, and the peaks are all in phase. They're all together. So A, they're going in as in phase, and they're coming out as in phase. The technical terms for going in and out are incident rays are when they go in, and reflective rays are when they come out. But then in B, they're out of phase when they are coming out, and it's hard to tell in this picture, but they're not doing the same thing. So they're not lined up perfectly, and that's what makes them out of phase. If you take physics, you'll study this more than we do in chemistry class, but the way that they cancel or they add on top of each other helps to see this. Other things that we learned from X-ray diffraction, the readouts when they take this with different crystalline structures, it will give us data about the bond lengths and the bond angles between the atoms or the molecules in the crystal. And so then when we see the experimental data of those, then that will help us to predict the molecular geometry. So is it sp2 oriented? Is it sp3 oriented? That kind of stuff. Okay. So this, we're not going to do it here, but that gives us some more information about our crystal lattice structures. A metallic crystal can be pictured as containing spherical atoms packed and bonded together equally in all directions. A lot of times we disregard the electrons in the metal structure because the electrons are the sea of electrons. So we have models, and we talked about this in Chem 1, that are called closest packing models, where the layers are packed so that each atom has 6 more surrounding it. Okay? So pull out the next model set. These were made by my TA, Rachel Payne, my first year teacher. Rachel Payne, my first year. Yeah. She painted these, and now they flake off, and it wasn't a great idea, but at the time it looked wonderful. Okay, so there's 2 types of closest packing. There's ABA and ABC. ABA, they just alternate A and B layers. So the A layers are all the same, the B layers are all the same, and they're just off slightly like so. The ABC is when you have 3 different options for the layers, and so the way that they fill in is a little bit more, it's different than ABA. Hopefully you guys know sequencing from math class to know like what the difference is there. These are pictured on page 466 and 467 in your textbook. When you have this type of closest packing, to make the unit cell, you actually have to just take a portion of it, and it's not going to be a cubic like the other ones were in the other pictures. It's actually going to be a hexagonal, or sorry, a rectangular prism. A rectangular prism for its unit cell. So the unit cell is the smallest building block of that repeating formation, but this would be showing how you do it for ABA, and then for ABC, in order to get the unit cell, it is cubic again, but you have to like rotate it on its side. It has to be tilted, and then that's where the unit cell comes from there. And then the last picture was what I have in my hand. That you have, this is the hexagonal close packing. This is one that you had to know in Chem 1, HCP, where when I said that there's so many atoms touching it, like if you, for this one, if you look there, if you look at the middle, there's 6 around it, right? And then we could put 3 all going to touch on the bottom, and then 3 more all on the all touching on top. So hexagonal closest packing actually has 12 atoms touching each atom, whereas the other 2, the ABA and the ABC, have only the 6 touching it based on the layers. So those are 2. Another type, which this was in that first picture, was face-centered cubic that we had in Chem 1, where on each side, each face of the cube, there's a centrally located atom, and in the center, there's nothing there. And then the other type is body-centered cubic. A body, there it is. Where the corners are not touching each other, supposedly, but instead they're all touching the central atom, and that's why it's in the center of the box. So that's why it's oh, look at this. Look at all these structures that somebody built. Yeah. Okay. Here's another one that somebody made out of ornaments. Back here. There's another one that could kill you. Stab you in the eye. So, we got some that are made out of Play-Doh that probably just throw away. Excuse me. So, yeah. So, we've seen these in Chem 1, but just to know, review those structures are good. Now, we talked a little bit about liquids versus solids yesterday. But let's look at how do the particles move within a solid versus a liquid, okay? The particles in liquids are in close contact, but they're continually moving and colliding. They flow against each other. That's part of how a liquid is the particles will flow against each other. When it's a solid, there is movement, but they are just vibrating in place, okay? So a liquid, they'll flow around. A solid, it will vibrate in place, so it's going to still hold its same spot. The arrangement and movement of particles are influenced by the nature and strength of the forces between the particles, and these are influenced by polarity, so what type of intermolecular force is there, hydrogen bonding, and temperature. So temperature is a measure of average kinetic energy, which we're going to talk about later in this unit. But when things are at higher temperature, more likely that they will be moving more. Okay, so from these two pictures, which one is the solid? This one. Ooh, I thought I was going to write. This one's the solid. And this one's liquid. Oh, it stopped when I started writing. That's sad. Okay. So the solid, did you see how they were rotating in place? Here, let's go back. There you go. So they're vibrating in place, but they're still holding their same spot. Whereas the liquid, I know it's like a terrible GIF, whatever it's called. But I think in the 8 years I've been teaching, I've never known how to say that right. Where they are moving around. And so they're supposed to be flowing, but it's hard to see that. But they are farther apart when they're liquid. Okay, so the solid and liquid phases for a particular substance typically have similar molar volume because in both phases the constituent particles are in close contact at all times. So this picture helps show that they have the same volume space because the solid is very ordered, right? Whereas the liquid is not, because the liquid can constantly move. But if we were to freely arrange the liquids to be like the solids, it would take up the same amount of space. And so that's why the volume is very similar for both of those. Like if I had an ice cube and melt it, probably the same amount. Are you okay?
I got you.
And last but not least, gases. So particles in gas phase are in constant motion and they're freely moving. Do you notice how they're not really close to anybody? The frequencies of collision and the average spacing between them are dependent on things like temperature, pressure, and volume, all of which we get into in 3.4, but not in this part. A gas is neither a definite volume nor a definite shape because A, the particles are in constant motion, and B, there are minimal effects of forces between the particles. So we just talked about the Coulombic forces for the first time in Chem 1 today. We did a Pogel. And so we know that like the protons from one atom are attracted to the electrons of the other atom, and that's how we get that interaction there. So a lot of times when we do calculations with gases, we forget about that, and we say it's not important, but it's really there. So we'll talk about that more in the next grouping of notes for the next quiz, but not for this quiz.